Centuries ago, while much of Europe was cloaked in intellectual twilight, a brilliant scientific revolution was already in full bloom elsewhere. This was the Islamic Golden Age, an era of astonishing discovery that would fundamentally shape our modern world. The scholar George Sarton noted that the main task of advancing human knowledge during this period was accomplished by Muslim thinkers, naming some of the greatest minds in philosophy, mathematics, and geography. You are about to uncover the hidden sciences born from this golden age and trace their incredible journey across continents. By the end, you will see the very blueprint of modern science, medicine, and technology in a completely new light. How did the language of algebra and the principles of the scientific method travel from Baghdad to Oxford, and why was their origin story nearly lost to time? What does it truly mean for human progress to be a shared inheritance? At the heart of this intellectual dawn stood the city of Baghdad, founded in the 8th century as the new capital of the Abbasid Caliphate. It rapidly grew into the world's most vibrant center of commerce, culture, and ideas. Under the reign of Caliph al-Ma'mun in the 9th century, this pursuit of knowledge became a state-sponsored mission. He and his successors poured immense resources into a single, transformative institution, the House of Wisdom, or Beit al-Hikmah. This was far more than a simple library. Picture a bustling academy, a translation bureau, and an observatory all fused into one dynamic hub. Scholars from diverse backgrounds, Muslim, Christian, Jewish, and Zoroastrian, worked side by side, united by a common language, Arabic, and a shared thirst for understanding. The quest for ilm, or knowledge, was seen as both a religious and a civic duty, a way to draw closer to the divine order of the universe. Historian Dmitry Gutas describes this not as a casual interest, but as a massive, systematic campaign to gather the world's knowledge. Agents were sent to distant lands to acquire precious manuscripts, paying for them with their weight in gold. The real magic, however, happened when these texts arrived. The scholars of the House of Wisdom did not merely copy ancient Greek, Persian, and Indian works. They engaged with them, debated them, and critically examined their claims. They corrected errors in Greek astronomical tables, expanded upon Indian mathematical concepts, and synthesized Persian medical knowledge. This culture of critical inquiry, of building upon the past rather than just preserving it, created a powerful new model of learning. It was this very environment, this fusion of global wisdom under one roof, that set the stage for a revolutionary chapter in human thought. The initial momentum was now unstoppable, and the first pioneers of this new science were ready to step into the light. Think about the last time you solved for x in a simple equation. That very act of balancing both sides to find an unknown quantity is a direct intellectual inheritance from a 9th century scholar working in the vibrant academies of Baghdad. His name was Muhammad ibn Musa al-Khwarizmi, and his groundbreaking book, The Compendious Book on Calculation by Completion and Balancing, did nothing less than give the world a new mathematical language. The title itself is the source of our word algebra, with al-jabr meaning restoration or completion. Before al-Khwarizmi, mathematics was largely about specific calculations in arithmetic or proofs in geometry. His revolutionary insight was to see the underlying patterns common to all kinds of problems, from trade to inheritance. He proposed a systematic method for solving linear and quadratic equations, a set of repeatable steps that could be applied universally. This methodical approach was so influential that his own name, al-Khwarizmi, was Latinized and entered the European lexicon as the word algorithm. His work also introduced the decimal positional number system to the Islamic world, which would later replace cumbersome Roman numerals in Europe. So what did this new science of algebra actually look like in practice? Al-Khwarizmi's methodology was beautifully structured. He taught how to reduce complicated equations to one of 6 standard forms, a process of simplification. Then came the balancing, the careful movement of terms from one side of the equation to the other to isolate the unknown. He even provided geometric proofs for his solutions, using the areas of squares and rectangles to demonstrate why his methods were true. This was not abstract theory created in a vacuum. It was driven by the needs of a sophisticated society. Consider the complex inheritance laws within Islam, which required precise calculations to distribute an estate fairly among many heirs according to specific shares. Solving these real-world puzzles demanded exactly the kind of logical toolset that algebra provided. Can you envision a world without this foundational language? Our entire modern world of engineering, computer code, and financial modeling rests upon the logical structures that Al-Khwarizmi first codified. This mathematical revolution provided the essential tools for measuring the cosmos itself. High above the bustling city, an astronomer peers into the night, his sight guided by an intricate brass instrument engraved with fine scales and rotating dials. This was not a solitary act of stargazing but a rigorous, systematic science, one that would fundamentally reshape humanity's cosmic blueprint. At the forefront stood al-Battani, a scholar whose meticulous observations over decades revealed subtle errors in the ancient work of Ptolemy, the Almagist. Al-Battani calculated the solar year with astonishing precision and provided a far more accurate measurement for the slow wobble of the Earth's axis, known as the precession of the equinoxes. His data did not just correct the Greeks, it provided a new foundation of celestial fact. The key tool for such work, and for countless daily applications, was the astrolabe. Perfected by Muslim scholars, this handheld marvel of brass plates and sighting rules was the portable computer of its age. Navigators used it to find their latitude, timekeepers determined the hour from the sun's position, and entire communities relied on it to know the precise times for daily prayers. It translated the abstract geometry of the heavens into practical, actionable information. This drive for accuracy fueled the creation of monumental state-funded observatories like those at Maragha and later Samarkand. These were not simple towers but vast scientific campuses where teams of astronomers, mathematicians, and instrument makers collaborated. They shared data, challenged each other's assumptions, and collectively built new planetary models that sought to fix the inconsistencies in Ptolemy's geocentric system. Their work, creating complex mathematical constructions to preserve the observed motions of planets, would later find its way to Europe, offering a toolkit for thinkers like Copernicus. The legacy of this collective effort is stunningly embodied by Ulugh Beg, a ruler who was also a passionate astronomer. At his great observatory in Samarkand, he and his team compiled a star catalogue so precise, detailing the positions of over 1,000 stars, that it remained the most accurate in the world for centuries. Can you consider how our modern sense of the cosmos rests upon this foundation of centuries of meticulous observation, of countless nights spent charting the slow dance of the heavens? This celestial mapping, this quest to understand light from the stars, was intrinsically linked to a parallel revolution in understanding light itself here on the ground. A simple glass of water reveals a profound truth. Look at a straw sitting in the glass and it appears bent at the surface. For over 1,000 years, the Greek explanation held sway, suggesting that rays emanated from our own eyes to touch the objects we see. But one man, working in 11th century Cairo, looked at this same phenomenon and saw not a puzzle but a flaw in the entire foundation of optics. His name was Abu Ali al-Hasan ibn al-Hasan ibn al-Haytham, known to the West as al-Hazan. He argued that the bending of light was not about vision leaving the eye, but about light itself traveling in straight lines and changing direction, or refracting, as it passed from one medium, like air, into another, like water or glass. This was a complete inversion of the ancient model. He laid out his revolutionary ideas in his monumental work, the Book of Optics. This was not merely a new theory, it was a new way of doing science. Ibn al-Haytham insisted that truth was not found in the books of ancient authorities but through systematic experiment and demonstrable proof. He wrote that the seeker after truth is one who suspends his judgment and follows the evidence. He questioned everything he read until he could test it for himself. This method of inquiry, testing, and building knowledge based on evidence is the very bedrock of the modern scientific method, and he was practicing it centuries before it became the standard in Europe. His experiments were models of ingenuity. To prove his intromission theory of vision, that light rays enter the eye to form an image, he used a dark chamber with a single pinhole, a camera obscura. He demonstrated that light travels in straight lines by projecting the image of an object outside, like a crescent moon, onto the opposite wall, inverted and perfectly clear. He meticulously studied reflection, detailing the angles at which light bounces off mirrors, and he explored the mathematics of refraction, creating the first accurate tables for how light bends. The practical legacy of this work is all around us. His deep understanding of how light behaves through curved pieces of glass laid the essential theoretical groundwork. Without his principles of optics, could anyone have later conceived of eyeglasses to correct vision, the telescope to bring distant worlds into focus, or the microscope to reveal a hidden universe teeming with life? Every time you use a camera on your phone, you are harnessing principles first proven by a man who trusted his own experiments over 1,000 years of accepted wisdom. His light did not stop at the borders of the Islamic world. It was a beacon that would soon shine directly into the heart of Europe, carried by travelers and translators who were about to bridge two intellectual ages. Yet this brilliant understanding of light was not confined to the stars or to lenses. It illuminated the halls of another revolutionary institution, one dedicated to the science of life itself. Walk through the gates of a 10th-century hospital in Baghdad or Cairo, and you would encounter a world of healing far ahead of its time. These were not simple sick houses but advanced medical centers, often offering care without charge, with separate wards for different illnesses, libraries for physicians, and even facilities for those with mental health needs. This organized, humane approach to medicine was the fertile ground from which two intellectual giants emerged. The first was Abu Bakr al-Razi, known in Europe as Rhazes. A brilliant clinician and chemist, his most enduring work was a vast medical encyclopedia called Al-Hawi, or the Comprehensive Book, but his true genius shone in his meticulous observation at the bedside. He left a landmark text, a detailed clinical description that allowed physicians for the first time to clearly distinguish between two similar illnesses, smallpox and measles. He documented the progression of symptoms, the fevers, and the distinctive rashes with such precision that his work became a cornerstone of differential diagnosis, the very art of telling one disease from another. Building upon this foundation came Ibn Sina, or Avicenna, whose monumental canon of medicine synthesized the entire medical knowledge of the ancient and Islamic worlds into a single, logical system. The canon was staggering in its scope, systematically covering anatomy, physiology, the nature of various diseases, and detailed treatments using hundreds of medicinal substances. It did not just repeat the teachings of Galen and Hippocrates. It critically evaluated them, correcting errors and introducing new insights, such as the understanding that tuberculosis could spread through the air and that some illnesses might be linked to contaminated water or soil. The canon emphasized the importance of experimental evidence and clinical trials, stating that the effectiveness of a drug must be verified through testing. For 5 centuries, this text was the primary medical textbook in European universities, the undisputed authority that trained generations of physicians. Can you trace the origins of modern medical ethics and our very concept of a hospital back to these pioneering halls? The legacy is profound. The rigorous, evidence-based approach championed by these scholars, combined with their drive for effective treatments, naturally fueled an equally ambitious pursuit in the workshops and laboratories of the time, a science dedicated to transforming matter itself. The search for the philosopher's stone, that legendary substance said to turn lead into gold, captivated minds for centuries. Yet in the workshops of the Islamic world, this mystical pursuit yielded something far more valuable than precious metal. It forged the very foundations of modern chemistry. At the center of this transformation stood Jabir ibn Hayyan, known in Europe as Geber. He insisted that true knowledge of matter came not from ancient books or mystical incantations, but from the hard, tangible evidence of the laboratory. His quest for an elixir of life drove him to invent and perfect the tools that would become standard for chemists for 1,000 years. The most crucial of these was the alembic, a sophisticated apparatus for distillation. Picture a heated flask connected by a tube to a cooling chamber, a setup designed to separate liquids based on their boiling points. This single piece of equipment unlocked a new world of substances. Jabir and those who followed his methods did not just dream of transformation, they performed it daily. They systematically classified materials into spirits, metals, and stones, and they documented the preparation of powerful new agents like nitric acid and sulfuric acid. These were not theoretical curiosities. They were practical tools for working with metals and other materials, enabling the discovery of entirely new compounds. His writings read like detailed laboratory notebooks, filled with precise recipes that any skilled practitioner could follow and reproduce. Can you see the profound shift here? The focus moved from why a change might happen in theory to how you could make it happen reliably, again and again. This experimental mindset found a beautiful and lucrative expression in the perfume industry. The distillation of rosewater and other fragrant essences became a major economic force, with scents traveling from Persian gardens to markets across the Mediterranean. This commercial demand for pure, concentrated floral waters drove constant refinement of the very chemical processes Jabir pioneered. Every bottle of perfume was, in its own way, a testament to a new, hands-on science of matter. The patient work of these early chemists, meticulously recording their results and improving their equipment, built the essential toolkit. The alembics, the furnaces, and the precise methods of filtration and crystallization they perfected were not lost secrets. They were tangible technologies ready to be carried forward, just as the intellectual treasures of the House of Wisdom were about to make their own great journey westward. That unified body of knowledge, the very blueprint for later revolutions, did not simply appear. It was built word by painstaking word in one of history's most ambitious intellectual projects. Fueled by a caliphal decree that viewed learning as essential to statecraft, the Abbasid leadership launched a massive, systematic campaign to gather the world's wisdom. Think of the practical needs of a vast empire spanning from North Africa to Central Asia. To manage trade, collect taxes, build canals, and care for its people, the state required advanced engineering, precise mathematics, and reliable medicine. This created a powerful, practical demand for the specialized knowledge contained in ancient texts. But the drive was also profoundly intellectual, a curiosity that boldly transcended linguistic and cultural barriers. At the heart of this effort was the master translator Hunayn ibn Ishaq, a Nestorian Christian whose name became synonymous with accuracy. He did not simply take a single Greek manuscript and render it into Arabic. His methodology was far more rigorous. He would seek out multiple source manuscripts, often traveling great distances to find them, and then carefully compare the different versions line by line. He worked to understand the precise meaning of each term, sometimes creating new Arabic words to capture concepts that had no existing equivalent. This was not a mechanical process of substitution. It was an act of deep scholarly interpretation. The goal was to produce an Arabic version that was not just a translation, but the most accurate and refined version of the original work possible. Once a text was translated, the process of engagement truly began. Muslim scholars did not treat these works as untouchable relics. They annotated them, debated their claims, and often corrected their errors. Historian Dimitri Gutas describes this not as passive preservation, but as an active engagement and enhancement of the source material. A perfect example is the translation of Ptolemy's great astronomical work, the Almagest. The team at the House of Wisdom did not just render its Greek prose into Arabic. They recalculated its astronomical tables, using their own advanced observations to correct its values and make its predictions far more precise. This massive, coordinated undertaking, spanning generations, created a unified and enriched corpus of knowledge written in a single, international language of science, Arabic. This vast library of translated and improved texts, covering everything from philosophy to physics, would become the direct intellectual inheritance of a Europe just beginning to stir from its long intellectual quiet. The bridge for this great transfer was already under construction, built not by armies but by scholars, travelers, and the shifting borders of empires themselves. The translated texts, now enriched with new commentary and corrections, needed a physical pathway into Europe. That gateway was not a single door but a vibrant, sun-drenched corridor of cultural exchange stretching from the Iberian Peninsula to the island of Sicily. In the cities of Al-Andalus, particularly Cordoba under the Umayyad Caliphate, a unique society flourished. Here, Muslims, Christians, and Jews lived side by side, creating an intellectual atmosphere that directly rivaled Baghdad in its brilliance. The Great Library of Cordoba was said to hold hundreds of thousands of volumes, a beacon of learning that attracted scholars from across the Mediterranean. This was not an isolated island of cooperation but a complex, working model of partnership that made the transfer of knowledge possible. The real engine of this exchange, however, was the legendary Toledo School of Translators. After the city passed into Christian rule, its rich Arabic libraries and its living tradition of scholarly dialogue became a magnet for European thinkers hungry for knowledge. They did not come as conquerors but as students. Figures like Gerard of Cremona traveled from Italy to Toledo specifically to seek out texts he knew were unavailable in Latin. He found a team-based working environment where a single book's journey from Arabic to Latin was a collaborative feat. A Jewish scholar might first translate the Arabic into the shared vernacular of Castilian, and then a Christian scholar would render that version into formal Latin. This was not a dry, mechanical process. It was a living conversation, a daily debate over the precise meaning of a philosophical term or a mathematical concept. Gerard of Cremona alone spent decades there, translating over 87 major works, including Ptolemy's Almagest from its improved Arabic version and Al-Khwarizmi's revolutionary book on algebra. Can you picture the scene, the shared workspace where the light of ancient Greek thought, filtered and amplified through centuries of Islamic scholarship, was finally being kindled into Latin? A similar dynamic unfolded in the Norman kingdom of Sicily under the enlightened rule of King Roger II. His court in Palermo was a mosaic of Arab geographers, Greek philosophers, and Latin administrators. This was a place where the latest astronomical data from Cairo could inform the design of a new church, and where Arab naval charts guided Norman ships. This continuous, daily interaction in these multicultural hubs provided the essential human network, the trust and shared purpose, required for ideas to cross a civilizational divide. The translated texts, carefully inscribed onto fresh parchment, were now ready. Their journey northward into the heart of a Europe on the cusp of its own great awakening would begin along the oldest roads on the continent. The thirst for this new knowledge created a new kind of European scholar, one willing to cross mountains and learn new languages for a single book. Gerard of Cremona, a scholar from Italy, heard whispers of Ptolemy's Almagest, a masterwork of astronomy he knew was held within Arabic libraries. He traveled to Toledo not as a tourist but as a dedicated student, learning Arabic specifically to uncover its wisdom. His personal mission grew into a lifetime project, resulting in Latin translations of over 70 major works, from Al-Khwarizmi's algebra to the medical compendiums of Al-Razi and Ibn Sina. He was not alone in this great work. The translation movement required powerful sponsors who recognized the strategic value of this advanced learning. Archbishop Raymond of Toledo actively supported the scholars working in his city, providing resources and legitimacy. Further east, the Holy Roman Emperor Frederick II, a ruler fascinated by science and philosophy, sponsored translations directly at his court, corresponding with Arab mathematicians and seeking out the latest texts. This was not merely a hobby for the elite. A powerful convergence of motives fueled this first wave. The 12th century saw a European intellectual reawakening, a growing curiosity that demanded new answers. Universities were emerging in cities like Bologna and Paris, creating a voracious demand for textbooks. Kings and religious leaders needed accurate calendars, better medicine, and advanced engineering. Possessing this knowledge offered a clear competitive advantage in statecraft, planning, and health. The translation process itself was a marvel of collaboration. A single text journey from Arabic to Latin was rarely a solitary task. It often involved a team, perhaps a Jewish scholar translating the Arabic into the local Castilian vernacular, and a Christian scholar then rendering that version into the formal academic language of Latin. This was a living, breathing dialogue across cultures, a daily debate over the precise meaning of a philosophical term or a geometric proof. Historians note that these translations were far from simple word-for-word copies. The scholars frequently added their own commentaries and glosses, interpreting the complex ideas for a European audience and integrating them with existing religious and classical thought. Another pivotal figure was Constantine the African. Arriving at the monastery of Monte Cassino, he brought with him a deep understanding of Arabic medical texts. There, he dedicated himself to translating works like the Pantagruel, a major medical encyclopedia, into Latin. Through his efforts, the sophisticated medicine of the Greeks, which had been preserved and expanded by Islamic physicians, was effectively reintroduced to Europe. The arrival of these hundreds of translated texts was like a sudden, brilliant sunrise after a long night. They provided the essential raw material, the very intellectual fuel, for a revolution in European thought. Yet this influx of new ideas would soon create a profound and challenging tension with the established intellectual order. A single manuscript's journey from a sunlit scriptorium in Cordoba to a chilly university hall in Paris was an epic in its own right. These textual caravans, transported by merchants and dedicated scholars across the Mediterranean, carried the intellectual wealth of an entire civilization. The most influential of these books became the new pillars of European learning. Ibn Sina's Canon of Medicine, a systematic encyclopedia of diagnosis and treatment, was translated into Latin and began its life in the West as a massive, expensive codex. Al-Khwarizmi's work on algebra, introducing a revolutionary logic of equations, traveled the same roads. Perhaps most transformative for philosophy were the extensive commentaries on Aristotle by Ibn Rushd, known as Averroes, which presented a coherent, rationalist interpretation of the Greek thinker that had been lost to Europe for centuries. The reception of these works in the budding universities of Bologna, Paris, and Oxford was a mixture of awe and deep unease. They offered answers to questions about the natural world that existing Latin texts could not, but their authority was foreign, and their conclusions sometimes challenged theological teachings. Yet their utility was undeniable. The Canon of Medicine, for instance, was so comprehensive and logically structured that it was adopted as the central medical textbook at the great schools of Montpellier and Padua. For 500 years, it remained the foundation of a physician's education, its diagnoses and treatments forming the core of medical practice. The material reality of these books tells its own story. Producing a single Latin copy of the canon was a monumental task, requiring teams of scribes in scriptoria to labor for months over costly parchment. The expense meant that such a volume was a treasure, often secured to a library desk for careful study. It is in the margins of these very books that we see the vibrant intellectual engagement of European scholars. Paleographers, experts in ancient handwriting, can trace the spread of ideas through these handwritten notes. A scholar in Paris might scribble a question next to a passage on human anatomy, while another in Oxford would carefully correct an astronomical table based on a newer observation. This physical evidence, the ink on the page, shows a living conversation across time and space. Can you grasp the immense power held within the bindings of a single book, how its journey could redirect the flow of human thought for centuries? This incoming tide of knowledge did not simply fill old libraries. It demanded entirely new vessels to contain its force. The lecture halls of 13th century Europe echoed with a new and vibrant energy. In the rising universities of Bologna, Paris, and Oxford, masters and students grappled with a flood of texts that offered a radically different vision of the natural world. This was the new Aristotle, but not as the ancient Greeks had known him. Europe received the philosopher primarily through the detailed, sophisticated commentaries of Muslim thinkers like Ibn Rushd, known as Averroes, and Ibn Sina, Avicenna. Their interpretations presented a universe governed by logical, discoverable laws, a direct challenge to the more mystical, Platonic framework that had long shaped European thought. This was not a quiet addition to the library, it was an intellectual transformation. The very structure of learning, the curriculum known as the trivium and quadrivium, was reshaped. The 7 liberal arts, grammar, rhetoric, logic, arithmetic, geometry, music, and astronomy, were suddenly supercharged. The geometry course was no longer just Euclid, it was now informed by Al-Khwarizmi's algebra. The astronomy class relied on the corrected planetary tables from Maragha. The medical faculty taught from Avicenna's canon, a text so vast it surpassed all previous Latin manuals. This new knowledge did not slot in neatly, it demanded a response, forcing a great synthesis between this powerful natural philosophy and the established tenets of Christian theology. In Paris, this tension grew into what historians call the Averroist crisis. the interpretations of Ibn Rushd suggested philosophical truths that could be reached by reason alone, even if they seemed to differ from revelations of faith. This created a deep and lasting conversation, a debate over the very boundaries between human reason and divine truth that would continue for generations. Yet, even amidst this exchange, the new tools were put to brilliant use. At Oxford, Robert Grosseteste and Roger Bacon began pioneering work on light and optics, and they explicitly credited their Islamic sources. Bacon praised the experimental method of Ibn al-Haytham, arguing that European scholars must learn from him. He wrote that this knowledge had been held in languages they did not understand, and that it was now their task to build upon it. This formal adoption by the university system for all its debates was the final, crucial step. It embedded the translated sciences into the very heart of European intellectual life, ensuring they would be copied, taught, and discussed for centuries, providing the essential foundation for what was to come. This deep tension between reason and revelation was the central intellectual drama of the medieval world. At its heart was a simple yet profound question. Could the truths discovered through logic and observation coexist with the truths received through faith? Into this charged arena stepped the Andalusian philosopher and jurist Ibn Rushd, known to the Latin West as Averroes. Living in 12th century Cordoba, he produced a monumental series of commentaries on Aristotle, works so clear and comprehensive that they became the definitive gateway to the Greek philosopher's thought for European scholars. His life's work was an ambitious project to build a lasting bridge between these two domains of knowledge. Ibn Rushd argued that religion and philosophy were not enemies but partners, two distinct paths leading to the same ultimate truth. For the general public, he explained, Scripture provided accessible guidance through stories and laws, but for those with the capacity for rigorous thought, philosophy offered a path to the same truths through demonstrative proof. When a passage in the Quran appeared to conflict with an established philosophical conclusion, he proposed it should not be taken literally but understood through allegorical interpretation. This was not a rejection of faith, but a defense of its deeper, rational meaning. He applied this method to some of the most challenging questions of his age. He defended the idea of the world's eternity, not in a way that denied a creator, but as a continuous emanation from a divine source. He explored the nature of the intellect, suggesting a shared, universal mind that individuals could connect with through learning. Most powerfully, he argued that philosophical inquiry was not just permitted, but was a religious obligation for those capable of it, a form of worship that honored the divine gift of reason. His ideas traveled to the budding universities of Europe and ignited a firestorm. Latin scholars, grappling with his powerful logic, sometimes misinterpreted his position, leading to the controversial concept of double truth. This was the idea that something could be true in theology while its opposite was true in philosophy. While this was a distortion of Ibn Rushd's actual belief in a single, harmonious truth, the concept itself became a flashpoint, forcing European thinkers to define their own boundaries. No one engaged with his work more deeply than Thomas Aquinas. The great Christian scholastic built his own monumental synthesis of faith and reason by directly wrestling with Ibn Rushd's arguments, adopting some and carefully rebutting others. The very structure of Aquinas' work, its methodical use of logic to explore theological questions, bears the clear imprint of this engagement. Can you see how this centuries-old conversation about the limits of human understanding still echoes in our modern dialogues between science and religion? The intellectual courage Ibn Rushd championed, the right to explore the natural world systematically without abandoning faith, provided the essential philosophical framework for the scientific revolutions yet to come. A disk of polished silver over 6 feet wide captured the entire known world in stunning detail. This was the Tabula Rogeriana, a map crafted in the year 1154 by the Muslim geographer Al-Idrisi for the Norman King Roger II of Sicily. For 3 centuries, it would remain the most accurate world map in existence, a testament to a cartographic tradition that understood the Earth not as a flat plane, but as a perfect, measurable sphere. Al-Idrisi's genius lay in his method. He did not rely on myth or ancient authority alone. He combined the geographical framework of Ptolemy with a flood of new, empirical data gathered from a network of Muslim merchants and travelers who journeyed across the globe. He interviewed them systematically, comparing their accounts of distant cities, trade routes, and cultural practices to build a reliable description of the world from the Atlantic to the Far East. His resulting book, The Recreation for Him Who Wishes to Travel Through the Lands, was a comprehensive geographical encyclopedia, and the Silver Planisphere was its breathtaking visual summary. This map was oriented with south at the top, and it depicted a world connected by knowledge. It showed the sources of the Nile, the contours of the Mediterranean with remarkable precision, and the sprawling extent of Asia, all plotted using a coordinate system of lines of latitude and longitude. Can you grasp the power of holding such a document, of seeing the planet laid out as a single, navigable whole for the very first time? This was not an isolated achievement. Islamic cartographers had long understood the Earth to be spherical, calculating its circumference with impressive accuracy and creating maps that were both scientific instruments and records of human commerce. When these works, including those of Al-Idrisi, were translated into Latin, they became state secrets and strategic guides. They provided the foundational data for European explorers, filling the empty spaces on their own rudimentary charts. The court of Prince Henry the Navigator in Portugal was steeped in these translated geographical texts, which informed his sponsored voyages down the coast of Africa. Even Christopher Columbus likely relied on maps derived from Islamic sources that presented a smaller Earth, reinforcing his fateful calculation that Asia lay just a manageable voyage to the west. Our modern map of the world, our very sense of global connection, was born from this systematic fusion of ancient theory and tireless, on-the-ground reporting. The ambition to chart the world so precisely was itself driven by another powerful force, the relentless innovation in machines and mechanics that was transforming daily life. The soft chime of a water clock in a 13th century palace marked more than just the hour. It signaled a revolution in mechanical thought. Behind these wondrous devices stood Ismail al-Jazari, a master engineer whose work represents the ultimate fusion of artistic beauty and practical science. Serving the Artukid court in Anatolia, al-Jazari did not merely build machines, he wrote them down. His book of knowledge of ingenious mechanical devices is a stunningly detailed medieval engineering textbook filled with instructions and diagrams for 50 elaborate inventions. Each machine was a symphony of moving parts, from automated musicians that played drums and cymbals to peacocks that pivoted and servants that offered towels and poured drinks. These were not just royal amusements, they were profound demonstrations of mechanical principles that would underpin the modern world. Al-Jazari's genius lay in his systematic application of components we now take for granted. He perfected the use of the crankshaft, a device that converts rotating motion into a back and forth movement, a cornerstone of every internal combustion engine today. He masterfully employed camshafts to control the timing of sequences, and his intricate use of valves and pistons in hydraulic systems was centuries ahead of its time. His double-action suction pump was a marvel of efficiency, capable of drawing water continuously with a single crank handle, a design that would directly influence later European engineers. Perhaps his most significant contribution was the segmental gear, a gear cut from a piece of a circle rather than a full wheel. This ingenious design allowed for the conversion of continuous rotary motion into intermittent motion, a crucial element for complex timing devices. His famous elephant clock, an international symbol of cultural exchange, used this very principle in its elaborate hydraulic system to mark the passing hours. These technical manuscripts, with their precise part-by-part instructions, did more than describe inventions. They transmitted a complete knowledge system. An expert examining these texts would note they functioned as a complete engineering curriculum, teaching future generations how to design, build, and troubleshoot complex machinery. The impact was immediate and vital. His water-raising machines, for instance, dramatically improved agricultural irrigation, allowing communities to lift water from rivers to fields with far greater efficiency. This direct link between mechanical innovation and societal benefit encapsulates the practical spirit of the age. Can you trace the lineage from Al-Jazari's automated peacocks, powered by water and clever gears, to the intricate clockwork automata that would later captivate the courts of Renaissance Europe? The same principles of precision mechanics that brought inanimate figures to life were now poised to transform the most intimate of human experiences, the art of healing. A medieval pharmacist measured his ingredients with a meticulous hand, his scales balanced against the precise weights of justice. This was the Sadalia, a place of healing where rows of ceramic jars held syrups, salves, and potent distilled liquids. Within this organized space, the ancient art of remedy was transformed into the modern science of pharmacology. Pioneering scholars like al-Biruni and Ibn Sina did more than just list plants and minerals. They created the first true pharmacopoeias, systematic encyclopedias that detailed the properties, preparation, and exact dosage of hundreds of medicinal substances. They classified everything from where a plant grew best to its effects on specific ailments, insisting on the purity and correct identification of every ingredient. This was knowledge built on a global network of trade and observation, introducing powerful new agents like camphor for comfort, senna as a gentle aid, and sandal wood for its calming fragrance into the European materia medica. But how could a patient in Cairo trust the medicine they received was both safe and effective? The answer lay in a revolutionary system of professional oversight. The profession of the pharmacist was formally separated from that of the physician, creating a dedicated expert in the preparation of drugs. This new profession was held to a high standard by the Mutazib, the public market inspector, who ensured scales were accurate, ingredients were not altered, and all practices met a strict code of quality. This was the world's first system of pharmaceutical regulation, designed to protect the public. The tools of the trade were just as advanced. The alembic, perfected by earlier chemists, was now used to capture the very essence of a plant. Through careful distillation, apothecaries produced intensely concentrated essential oils and created the first reliable alcoholic extracts, which could preserve the active properties of herbs for much longer periods. To make these powerful medicines easier to take, they developed delightful new forms like the sweet, viscous syrup and the refreshing julep, a fragrant water infused with healing herbs. One of the most famous products of this sophisticated art was theriac. Originally a Greek compound, Islamic physicians refined it into an incredibly complex universal preparation, sometimes containing over 60 ingredients including various botanical elements, opium, and dozens of spices. This revered medicine became a staple in European apothecary shops for centuries, its recipe a closely guarded secret that symbolized the pinnacle of the compounder's skill. When you look at the cough syrup or pain relief gel in your own bathroom cabinet, can you trace their origins back to these bustling medieval pharmacies? to the first time a healer carefully measured a dose of camphor or distilled the essence of a rose. This systematic approach to formulating and standardizing medicine was a direct response to a deeper, more fundamental need, the desire to understand the intricate machine these remedies were meant to support, the human body itself. A detailed ink drawing from a 13th century medical text reveals the human jaw with remarkable clarity, each tooth precisely rendered and the bone structure carefully illustrated. This was not an artist's impression, but a scientific guide from the Islamic world, a visual reference that offered European physicians a clearer view of anatomy for generations. The master behind this empirical approach was Abu al-Qasim al-Zahrawi, known in the West as Abul Qasis. His life's work, a monumental 30-volume medical encyclopedia called Al-Tasrif, included an entire section dedicated to the art and science of surgery. For 500 years, this surgical manual stood as the unchallenged authority in European medical schools, its influence so profound that it shaped the practice of surgery itself. Al-Zahrawi's philosophy was rooted in direct, hands-on observation. He dismissed surgery based only on theory, insisting that a physician must learn from experience and see with their own eyes. His writing reads like a master craftsman guiding an apprentice, filled with careful descriptions of methods for everything from setting broken bones to addressing bladder stones. He detailed the use of cauterization to manage bleeding and help prevent infection, a vital technique long before modern antiseptics. His most lasting contribution may be the wide array of tools he designed and illustrated. He described over 200 specialized surgical instruments, from forceps and bone saws to intricate probes and needles. Many are clearly recognizable as the direct ancestors of instruments used in operating rooms today. He pioneered the use of catgut for internal stitches, a material the body could safely absorb. His work included advanced approaches for dental care, such as cleaning teeth and replacing missing ones with artificial ones shaped from animal bone. He recorded a method for addressing cataracts and performed complex procedures to extract stones from the bladder. These were not vague suggestions, they were step-by-step instructions, complete with detailed drawings of each scalpel, retractor, and syringe. These illustrations were not decorative, they were technical blueprints. A European instrument maker, even one who could not read the Arabic text, could look at the clear, precise drawings of a syringe for bladder irrigation or a scalpel for a specific incision and faithfully reproduce the tool. This visual language allowed sophisticated technology to cross cultural and linguistic barriers. Can you imagine the trust a patient had to place in a surgeon's hands, and how a single, well-illustrated manual could mean the difference between a successful procedure and a difficult outcome? The influence was direct and openly acknowledged. Centuries later, the great French surgeon Guy de Chauliac cited Al-Zahrawi more than 200 times in his own surgical texts, ensuring these methods remained the standard of care. This practical, hands-on mastery of the physical body was perfectly complemented by a more abstract, yet equally revolutionary form of logic. The very logic that guided the surgeon's hand was itself shaped by a more fundamental revolution, a science of how we know what we know. Long before the European Renaissance, Ibn al-Haytham articulated a systematic process for uncovering truth, a methodology that would become the bedrock of modern science. His journey began not with certainty, but with a profound and necessary doubt. In his work Doubts Concerning Ptolemy, he wrote that the seeker after truth is not he who studies the writings of the ancients and, following his natural disposition, puts his trust in them, but rather he who suspects his faith in them and questions what he gathers from them. He argued that truth was sought for its own sake, and those who were engaged in its quest were obligated to question everything. This was a radical stance, a deliberate break from relying on the authority of revered ancient texts. His method unfolded in a series of deliberate stages. First came observation of the natural world, a careful and unbiased gathering of information. From these observations, he would form a hypothesis, a proposed explanation for the phenomenon. The crucial next step was to design a controlled experiment to test that hypothesis, isolating variables to see what truly caused the effect. Finally, he used mathematical analysis to interpret the results, seeking a precise and quantifiable understanding. His famous camera obscura experiment is a perfect illustration of this entire process in action. He hypothesized that light travels in straight lines. To test this, he set up a dark chamber with a single, tiny pinhole. When light from a crescent moon passed through this pinhole, it projected an inverted image of the crescent onto the opposite wall. This was a controlled, repeatable test that anyone could perform, and its result definitively proved his hypothesis, while disproving the ancient theory of light emanating from the eye. This insistence on empirical verification and reproducible results is the very heart of the scientific method we know today. Historians of science note that this structured approach to inquiry is perhaps the most profound and enduring contribution of the era, a true science of science. Can you envision a world where knowledge advanced only through debate and deference to authority, without this disciplined framework of questioning, testing, and proving? The principles Ibn al-Haytham championed would later echo in the work of Galileo and Francis Bacon, providing the essential toolkit for understanding everything from the smallest particles to the grandest cosmic structures. Every Muslim, no matter where they stood on earth, faced a single unifying direction in prayer, the Qibla toward Mecca. This spiritual practice presented a remarkable mathematical challenge, one that encouraged scholars to see the world not as a flat surface, but as a perfect sphere. To calculate the precise bearing from a city like Cordoba or Samarkand required a new kind of mathematics, a geometry of triangles drawn on the surface of a globe. It was within the great observatories at Maragha and Samarkand that this science of spherical trigonometry was perfected into a powerful tool. Scholars like Nasir al-Din al-Tusi and al-Kashi moved decisively beyond the earlier Greek chord function. They defined all 6 trigonometric functions we use today, sine, cosine, tangent, and their reciprocals, as pure ratios within a right-angled triangle. This conceptual leap was monumental, transforming trigonometry from a collection of geometric ideas into a flexible computational system. To make this system practical, they produced incredibly detailed and accurate trigonometric tables. These were the advanced tools of their age, large volumes filled with numbers that allowed an astronomer to instantly look up the sine of an angle for any calculation, saving many months of careful work. Al-Kashi's pursuit of precision was legendary. He calculated the value of pi to 16 decimal places, a record of accuracy that would stand for nearly 200 years. His method was one of brilliant perseverance, inscribing polygons within a circle with over 800 million sides to narrow down the value. Meanwhile, Al-Tusi made a breakthrough that would resonate for centuries, a geometric device now known as the Tusi couple. Imagine a small circle rolling perfectly inside a larger circle that is twice its diameter. Al-Tusi proved that a single point on the rim of the smaller circle would oscillate back and forth in a perfect straight line. This was a mathematical model that generated linear motion from circular motion, a concept that would later become fundamental to astronomy. When these advanced trigonometric texts and tables were translated into Latin, they provided European mathematicians with a ready-made computational toolkit. Can you see the direct line from these spherical calculations to the work of Nicolaus Copernicus? Historians have noted the striking similarity between the mathematical models Copernicus used to explain the orbits of planets in his heliocentric theory and the models developed by Al-Tusi and his colleagues at Maragha. It appears he had access to the very techniques that solved the problem of compound circular motion. The next time a navigation app on your phone pinpoints your location or a spacecraft uses a gravity assist to slingshot around a planet, consider the invisible architecture supporting it. This elegant language of ratios and spherical angles, refined to answer a call to prayer, ultimately gave us the power to chart our own course among the stars. This mathematical sophistication was mirrored by an equally advanced understanding of the physical world. A thrown ball arcs through the air, a simple act that once posed a deep intellectual challenge to the ancient world. Aristotle had taught that an object's motion required a constant force from a direct physical mover, yet when a stone leaves the hand, what force pushes it forward? This puzzle occupied some of the finest minds of the Islamic world, who began to systematically question the Greek master's physics. In the 11th century, Ibn Sina, known as Avicenna, proposed a novel concept he called mail, or inclination. He suggested that a mover imparts something to the object, an internal tendency to continue moving. This idea was a significant departure from Aristotle, but it was in the following centuries that the theory truly matured. The Andalusian thinker Ibn Bajjah, known as Avempace, and later scholars in the 14th century, developed this into a fully formed theory of impetus. They reasoned that a projectile, once set in motion, carries within itself a certain power, a force impressed upon it by the original thrower. This impetus is what keeps it moving, not some mysterious push from the surrounding air, as Aristotle had argued. The motion only ceases when this internal force is gradually worn down by external resistances like friction or air resistance. Think of a wheel set spinning. It continues to turn long after the hand that pushed it is gone, its stored impetus slowly dissipating. This was a revolutionary framework, providing a coherent explanation for everything from a loosed arrow to a falling weight. It directly addressed the problem of projectile motion that had troubled natural philosophers for centuries. These debates were not purely theoretical. They extended to fundamental questions about the nature of the cosmos itself. Scholars vigorously discussed whether a vacuum was possible and why objects of different weights fell at seemingly different rates, laying the groundwork for later studies of free fall. The significance of this intellectual shift cannot be overstated. The theory of impetus was a crucial conceptual bridge, the essential precursor to the principle of inertia that would later become a cornerstone of Newtonian physics. It moved scientific thought away from the idea that rest was a natural state requiring no explanation, and toward the understanding that a body in motion tends to stay in motion. How many of the foundational ideas we attribute to later European scientists were, in fact, nurtured through centuries of collaborative debate across cultures? The physics of motion was not born in a vacuum, but was part of a vast, interconnected web of knowledge that linked the motion of a thrown ball to the precise rotation of the celestial spheres above. A single scholar's day could begin by charting a star's path with spherical trigonometry, then apply those same mathematical principles to design a more accurate astrolabe in his workshop, and end by consulting a newly translated medical text that relied on precisely measured herbal extracts. This was the reality of the Islamic Golden Age, a world where the sciences were not isolated islands of thought but a single, vibrant continent of knowledge. The lines we draw today between mathematics, medicine, and mechanics were utterly foreign to these thinkers. Their progress was a cascade where a breakthrough in one field would inevitably spill over and nourish all the others. Consider the practical journey of a single innovation. The development of advanced algebra by scholars like Al-Khwarizmi did far more than solve abstract equations. Its logical structures provided the foundation for elaborate new systems of cryptography, securing important state communications. Those same algebraic methods brought unprecedented precision to the complex calculations required by Islamic inheritance law, ensuring fair and mathematically sound distribution of estates within large families. This mathematical toolkit then became essential for astronomers who used it to compute planetary positions. Their resulting star charts, in turn, provided the celestial data that geographers used to calibrate maps and navigational guides. It was an endless, fruitful cycle. This interdisciplinary spirit is perfectly embodied by the towering figure of al-Biruni. In the 11th century, he produced works of stunning breadth, mastering astronomy, mathematics, geography, and even the then nascent study of comparative religion. He calculated the Earth's circumference with remarkable accuracy by applying trigonometric formulas to his observations from different mountain tops. He meticulously recorded the customs, calendars, and scientific knowledge of India, blending anthropology with geography. For al-Biruni, every field of inquiry was a different window into the same unified reality. Expert historians note that this holistic approach was the engine of its innovation. When a physician like al-Razi was also a practicing chemist, he could approach disease with a unique perspective, experimenting with purified substances and distilled remedies. When an engineer like al-Jazari understood advanced geometry, he could design the complex gearing in his water clocks with breathtaking precision. This culture encouraged looking at a single problem through multiple lenses, often leading to solutions that a specialist confined to one discipline might never have conceived. The great gift passed to Europe was not merely a list of facts or a catalogue of inventions. It was this very model of knowledge itself, a vision of an interconnected web where every discovery strengthens the whole. This integrated worldview, carried north on the very roads that connected empires, would provide the essential mental framework for the thinkers of the Renaissance, who themselves would strive to become masters of all the arts and sciences. Yet the very system that enabled this flourishing proved fragile. The slow fade of the Golden Age was not a sudden collapse but a gradual dimming, a complex unraveling fueled by pressures both from within and beyond its borders. For centuries, the great caliphates had provided a stable political and financial foundation, but this unity began to fracture. Across the Islamic world, large, centralized empires splintered into smaller, competing states. With this political fragmentation came instability as rival dynasties fought for control. The magnificent libraries and observatories, once sustained by the vast treasury of a unified empire, now found their funding severed or inconsistent. As scholars' work relied on patronage, and as royal courts turned their attention and resources toward constant military defense, the ambitious, long-term projects that defined the era became difficult to sustain. This internal weakening left the heartlands vulnerable to an external storm gathering on the eastern steppes. The Mongol invasions of the 13th century were a cataclysm. In 1258, the army of Hulagu Khan besieged and captured Baghdad, the very cradle of the Golden Age. The city's libraries, including the legendary House of Wisdom, were destroyed, and countless manuscripts were lost in the waters of the Tigris. The event in Baghdad stands as a powerful symbol of this devastating transition, a moment from which the central Abbasid intellectual project never truly recovered. While scholarship continued in other centers like Cairo and Damascus, the loss of this central hub and its accumulated resources was a blow from which the unified scientific endeavor could not fully heal. Alongside these political and military shocks, a subtle intellectual shift was also underway. In some circles, a more cautious approach to philosophy and certain natural sciences began to gain influence. The once confident synthesis of faith and reason, championed by thinkers like Ibn Rushd, faced growing scrutiny. Some theological interpretations began to view philosophical inquiry with suspicion, concerned that its conclusions might challenge religious doctrine. This was not a universal turn against all knowledge, but it did create an environment where the most speculative and ambitious scientific pursuits could be viewed as less of a priority. Economic currents also turned against the scholars. The great trade routes that had once funneled wealth and ideas into the Islamic world began to shift. New sea passages and economic crises internally diminished the vast fortunes that caliphs and viziers had once lavished on science. The generous patronage that allowed a man like al-Jazari to spend his life designing intricate automata, or that funded a massive observatory for Ulugh Beg, gradually dried up. Historians emphasize that it was this confluence of factors, political instability, foreign invasion, shifting intellectual currents, and economic decline, that collectively eroded the institutional support for science. The tradition of learning itself never died, it simply transformed, continuing in madrasas and courts across the Muslim world. But the era of grand, state-sponsored scientific revolution had passed. And as this light slowly faded in one part of the world, it was already being kindled into a new flame in another, carried forward on the very manuscripts that had escaped the destruction. The brilliance of the European Renaissance did not ignite from nothing. It was a flame carefully kindled with embers carried from the intellectual furnaces of the Islamic world, a direct inheritance that provided the very tools for Europe's own Great Awakening. Long before the age of Leonardo and Copernicus, a crucial preparatory phase known as the 12th century Renaissance saw European scholars in places like Toledo and Sicily eagerly translating the Arabic texts that would become their new curriculum. This was the essential groundwork, the gathering of raw intellectual material that would fuel creative explosions for centuries to come. When we examine the notebooks of key Renaissance figures, we find their engagement with this legacy is explicit and profound. The astronomical models of Nicolaus Copernicus show a striking resemblance to the mathematical techniques developed by astronomers at the Maragha Observatory, suggesting he had access to the very tools that solved the problem of planetary motion. Leonardo da Vinci's intricate designs for gears, water pumps, and automated machines echo the engineering principles detailed centuries earlier in al-Jazari's Book of Knowledge of Ingenious Mechanical Devices. His anatomical drawings, seeking to reveal the inner workings of the human body, follow a path of empirical observation first championed by the physicians of the Islamic world. In medicine and chemistry, the radical thinker Paracelsus explicitly turned away from older doctrines, embracing instead the experimental alchemy of Jabir ibn Hayyan and the precise pharmacology of Ibn Sina. The evidence of this lineage is etched into the language of European science itself. The Latin names Avicenna, Averroes, and Alhazen were cited as authorities in university lectures for hundreds of years. Their original Arabic names, Ibn Sina, Ibn Rushd, and Ibn al-Haytham, were the minds behind the texts. Technical terms like algebra, algorithm, alembic, and zenith entered European vocabularies directly from Arabic, each word a fossil of a transferred concept. An expert perspective clarifies that this inheritance was not just a collection of facts, but a complete toolkit. It provided the foundational texts, the rigorous experimental method of Ibn al-Haytham, and the vast stores of astronomical data that allowed Europeans to first learn, then question, and eventually build beyond their teachers. This influence is beautifully illustrated in the world of art. the revolutionary development of linear perspective, which allowed painters to create stunning illusions of depth and realism on a flat canvas, was a direct application of the optical principles laid out by Ibn al-Haytham in his Book of Optics. His mathematical understanding of how light travels in straight lines and enters the eye provided the scientific basis for an artistic revolution. The stage was now set for the next great leap in human thought, but its foundations, from the artist's studio to the astronomer's tower, were unmistakably laid centuries earlier and half a world away. The word algorithm powers our digital world, yet its namesake, the scholar Al-Khwarizmi, remains a quiet presence in our collective memory. This absence is not a simple oversight but a profound historical question. How could such a significant chapter in human knowledge become a footnote? The answer lies partly in a powerful narrative that took root in Europe, one we now call Renaissance exceptionalism. This was the compelling but incomplete idea that Europe's scientific rebirth was a unique, self-contained event, springing solely from its own classical past and innate creativity. To make this story work, the extensive intermediate chapters, the centuries of transmission and transformation, had to be minimized or written out entirely. The process began with the translators themselves. Eager to claim this powerful new knowledge for Christendom, many European scholars engaged in a quiet but systematic reshaping of identity. They Latinized the names of thinkers, turning Ibn Sina into Avicenna and Ibn Rushd into Averroes, effectively presenting them as honorary ancients. Their original identities and the vibrant intellectual culture that produced them faded into the background. These translated texts were then taught for centuries in European universities as authoritative sources, but their origins were rarely, if ever, highlighted. This set a pattern of omission that would harden over time. The colonial era further cemented this Eurocentric view, as histories were written that portrayed European advancement as an inevitable linear progression, often contrasting it with narratives about other parts of the world. This created a deep and lasting divide in how we perceive our shared scientific heritage. Contemporary historians like George Saliba and Sonia Brents are now carefully unraveling this complex story, recovering the lost narrative and weaving it back into the fabric of world history. They remind us that figures like Robert Grosseteste and Roger Bacon openly praised their predecessors, but later generations chose to forget this connection. Why does correcting this record matter so deeply? It transforms our understanding of human progress from a story of isolated genius to one of global collaboration. Acknowledging this shared achievement allows us to see the modern world not as a product of one civilization, but as our collective inheritance, built over centuries by countless hands and minds across continents. The numbers on this screen are a direct echo from that golden age. Every digit from 0 to 9, the very foundation of our mathematics and technology, traveled from India into the Islamic world, where scholars like Al-Khwarizmi championed their use. He did not merely adopt these numerals, he wrote the definitive book on how to use them, demonstrating their breathtaking superiority over Roman numerals for complex calculation. This Hindu-Arabic numeral system, with its revolutionary concept of place value and the profound inclusion of zero, was his vehicle for introducing algebra to the world. And from his own name, Al-Khwarizmi, we derive the term for the logical sequences that govern our digital existence, the algorithm. Your social media feed, your navigation route, every piece of code that shapes modern life is built upon a logic first systematized over 1,000 years ago. Look up at the night sky and you are still using their map. The bright star Betelgeuse derives from the Arabic phrase for the giant's hand, while Aldebaran means the follower, forever trailing the Pleiades cluster. These are not mere translations, they are living labels from the star catalogues of al-Battani and Ulugh Beg, whose observations first charted these celestial bodies with precision. The structure of learning itself bears their imprint. The medieval European university, with its endowed chairs, its system of degrees, and its emphasis on a structured curriculum, was profoundly shaped by the earlier model of the madrasa. Even the humble camera on your phone has a conceptual lineage that runs in an unbroken line through the Renaissance artists who studied perspective, back to the darkened chamber and the single pinhole that Ibn al-Haytham used to prove his theories of light. This is not about assigning historical credit, it is about recognizing a fundamental truth of human advancement. As the physicist Jim Al-Khalili has reflected, the science we take for granted today, from the rules of optics to the very ethos of rational inquiry, owes an immense debt to the multicultural scholars of the Islamic world. Our progress was never a solitary sprint, but a continuous relay across civilizations. The legacy is not locked in old books, it is alive in every calculation, every diagnosed illness, and every time we look to the stars and call them by names given to them by ancient watchers of the sky. Our journey has traced a path of light from the House of Wisdom to the halls of Oxford, following the careful hands that carried ancient wisdom forward. The hidden sciences of algebra, optics, and empirical medicine were never truly lost. They were preserved, translated, and enriched across cultures, becoming the essential foundation for the world we know today. This narrative dismantles a narrow, solitary view of progress, revealing a profound and beautiful reality. Human civilization is not a series of isolated triumphs, but a single, collective project woven from the contributions of countless peoples across continents and centuries. The philosopher Ibn Rushd offered a timeless insight when he observed that ignorance leads to fear, fear leads to hatred, and hatred leads to conflict. He called it an equation, and understanding our shared intellectual heritage is a powerful antidote to that first variable, ignorance. It is an invitation to look more deeply at the origins of the modern world, to see the interconnected threads in everything from the numbers on a screen to the names of the stars. Let us carry forward the very spirit that defined that golden age, a spirit of boundless curiosity, respectful exchange, and the courageous pursuit of truth. If this exploration has reshaped your view of our shared past, we would love to hear your reflections in the comments. Subscribe to join us as we continue uncovering the hidden connections that shape our world.